right? This t is m1 v squared over r. Could also be m1 omega squared r. Doesn't matter. Either one works. This t and this is m2g. So, of course, I've done some forces here, some forces there. So we get m1 v squared over r equals m2g. So v is equal to the square root of m2gr over m1. Then, when we ask ourselves, what is the definition of v? V is equal to 2 pi r over the period. So I can set these two equal to each other, and I get 2 pi r over the period equals the square root of m2gr over m1. Then from this, I can say period is equal to 2 pi r over the square root of m2gr over m1. Then that can become 2 pi r times the square root of m1 over m2gr. This r can become r squared in here, which cancels there, and we get the answer that we're looking for. So now on to part B. Here, if they want us to solve for g, so if I took that that thing which said p is equal to 2 pi times the square root of m1r over m2g. Just double check to make sure that's the right thing. 2 pi m1r over m2g, so that's right. Okay. So then this, I can solve for g, moving that to 2 pi, squaring that, and getting rid of this. So then we get g is equal to m1r over m2 times p over 2 pi squared. Okay, so that's our g. Now, this is a crazy thing because the things that are in this problem that are variable are m2 and p. So m1 and r are both constants. So the top is a constant. If I factor out the constants, it's like I get actually, let me rewrite this. If I square the bottom, I get m1r over m2 p squared and then 4 pi squared on the top. All of that's a constant. So basically, I'm getting m1r 4 pi squared times 1 over m2 p squared. So what we've got is, if you'll allow me, if I say g is some constant c times 1 over m2 p squared. So we have to get the slope of this graph to be 1 over m2 p squared. And so the sneaky way to do that, because when we do a graph like this, right, usually if we have this and we want this slope right here, generally, if we do something like this, it's rise over run, so it's going to be a over b. So whenever we have something in the form of something equals a over b, we can get the slope pretty easily rise over run. Here, we have something in the form of, I don't know, like g is equal to 1 over a times b. So how do we get this to work? We just have to rearrange this so it's 1 over a divided by b. So in this case, what happens is we say g is c times 1 over p squared over m2. So what we've done is taken p on the bottom, turned it into 1 over p on top. So then our a here becomes 1 over p squared, and then our b is m2. So we just need to do 1 over p squared here, and then graph those values, and then once we graph them, we'll be good. Now in regards to graphing, in regards to this chart, If you follow directions, things will be fine. Plot your points however they come out. Put a best fit line, best fit, do not connect the dots. Label your axes and have units. You also want to make sure this has a label with units. You also want to make sure that your graph takes up as much of the paper as, or the chart as possible. You don't want some little tiny graph in the corner. And then once you take the slope is going to be equal to 1 over m2 times p squared. So in order to get g, we need to take the slope times that constant value, which was 4 pi squared m1r. So all of that plugged in times g, and we will get the value that we're looking for. All right, so that is the first problem. Now let's go to the second problem with the roller coaster. So here, they want to know on the track at which point is the maximum speed of the car attained. So at which point on the track is there as little potential energy of gravity as possible? That's going to be here at point P. So I label it P because that has the least amount of potential energy. Then what is the value of the velocity at this point? Well, I'm just going to use energy now. I'm going to say this is PEA, and then down here I said there was no potential energy at the bottom, so it's got to be KE. Okay, and so my PEA is going to equal my KE at point P. And so I'm going to get mgh equals 1/2 mv squared. My m's cancel. I get v is the square root of 2gh. If you remember, going all the way back to chapter 2, the velocity for anything that falls near Earth is the final velocity of starting from rest is 2gh. So we can use that here, plug in all our values, and we'll get the appropriate velocity at the bottom. Then it says calculate the speed VB at point B. So now we want the velocity here. So I have to do my energy statement again, but from a different place. So I'm going to start with PEA again, because it started from the top. Also, we were given that VE is 0, so I never had to worry about that KE at A. And I say that's going to equal PE at point B plus the KE at point B. So we get mgh equals mg, I guess we should say, well, no, I'm going to do this, try to do this the easy way. And do you see that delta PE is going to equal to KEB? And delta PE is going to be mg delta y, and that's going to equal 1/2 mv squared. So that's going to leave me v is the square root, because remember, v is the square root of 2gh. So that's going to give me 2g delta y. And then in this case, that gives us the velocity that we're looking for at point B. On the figure of the car below, draw and label the vectors, so that's pretty easy. We've got Fn going down, and we've got Fg going down. All right? And so we move on to the last parts of the problem. Calculate the magnitude of the forces identified. So I'm going to say the sum of those forces is equal to v squared over r. Those two forces are going to be Fn plus Fg, which equals mv squared over r. So we say Fn, Fg we know, right? Because Fg is just going to be mass times gravity. And then that comes out to be whatever, like 7,000 newtons, because it's 700 kilograms. So then Fn is going to be mv squared over r minus mg, which comes out to the value we're looking for, around 21,000 newtons. Then the question says, suppose that friction is not negligible, how could the loop be modified to maintain the speed? So remember, our roller coaster goes like this, it comes up, then makes a loop, and then goes here. So there is this distance underneath that could be changed. Basically, what has to happen is we need more KE, right? How do I get more KE at this point? I either raise this top or I drop this bottom, because I need delta y to increase. If I increase delta y, then I will increase the kinetic energy that I get out of it, so that when the work done by friction happens, I end up with the right amount. just so we can see how that works, if I say PEA equals PEB plus KEB, I have to account for that work done by friction right there, because that's the thing that's killing us and taking away from our kinetic energy. So if I solve all this out, I'll get some final velocity in which, some velocity statement in which the work done by friction is subtracting from the kinetic energy, and therefore I have to increase my potential energy to get that kinetic energy to be high enough. There you go. All right, that's it. Remember that these, this is 2004. The first problem was 2009, right there. And both of these are online, and you can ask me any questions.